If AI learns to reason, they'll replace most, if not all, scientists and mathematicians very quickly. This year's Nobel Prizes gave us a taste of this. Not only did the Nobel Prize in Physics go to the development of AI, the one in chemistry went partly to DeepMind for their AI-driven advancements in understanding protein folding. In the future, I believe, not only will pretty much all of science be done by AI, it'll become a requirement to prevent cognitive biases. Indeed, 2 papers just came out in which computer scientists have presented the first full AI scientists. Oh yes, fellow scientists, you have no idea what's about to hit you. We no longer need to ask which jobs AI will replace first, because it's already happened. The jobs that seem to have been replaced most so far are those requiring fast text generation, either to feed news websites or for chatbots. Though it's questionable whether AI is currently much of a benefit for news websites. The US tech site CNET, for example, began using AI to push out news at the end of 2022. As a competing website happily reported, the articles were riddled with mistakes. Last year, it turned out that Cosmos magazine had been using AI to create some articles, and promptly complaints rolled in. Though most of the complaints come from journalists at risk of being replaced. And this is just what AI can do now. I'd be surprised if not OpenAI and Meta and many other places are working on integrating math software into large language models, and probably a bunch of other tools as well, like graphics software. And once they've done that, they'll come for scientists. This is because in most fields of science, standard math software is all you need. Yes, there are exceptions to this. Maybe if you're cooking up amplituhedra in the basement, you don't want AI company. But let's be real, for most disciplines, calculus and statistics is more than enough. And given that, an AI could, for example, design an online questionnaire, recruit people, analyze data, and publish a full paper all by itself. This isn't an entirely new idea, of course. People have used AI to formulate hypotheses and execute automated experiments before, but there was always a human involved at some stage. Now we have, for the first time, an end-to-end service, a chain of AI processes that emulates a scientist's entire work, from hypothesis generation to publication. In a paper that just appeared, computer scientists present the first AI scientist and write that it's taking us closer to a world where endless affordable creativity and innovation can be unleashed on the world's most challenging problems. Each idea is implemented and developed into a full paper at a meager cost of less than $15 per paper, illustrating the potential for our framework to democratize research, or more likely to flood research with crap, though at least it'll be democratically flooded by crap. Their AI scientist is just a sequence of tasks executed by existing large language models, from brainstorming to literature research, laying out a research plan, executing it, and writing a paper, though they seem to have skipped the part where you question your life choices because it's 3 a.m. and you still haven't found that minus you were looking for. The research area the AI scientist worked on was, of course, AI science. They then had an AI reviewer scrutinize the AI-generated papers about AI research and found that Anthropic's Sonnet 3.5 consistently produces the best papers, with a few of them even achieving a score that exceeds the threshold for acceptance at a standard machine learning conference that presumably will be attended by AIs. They did not publish the AI-generated papers, but seeing that their code is open source on GitHub, I have no doubt others will do it for them. The second group took an entirely different approach to AI science. They generated a computer game with a virtual environment that they called Discovery World, with discoverable laws that this artificial world is governed by, including chemistry, physics, epidemiology, and rocket science. In this virtual virtual world, they had quests to discover these laws. For example, that people fall ill and you have to figure out why. Then they had GPT-4o and humans try to discover these laws. They found that the humans succeeded more often, especially when it comes to actually completing the research. So at least for now, we have somewhat of an edge. You might find this all a little silly and implausible, but I'm convinced that once AI learns to reliably perform math calculations, we'll see a flood of AI-written research articles. I can think of many calculations that can be automated in my research area, such as finding new solutions to Einstein's field equations, which is mostly trial and error, or the state-of-the-art for inventing new particles to explain anomalies in high-energy physics. There are thousands of people who currently live from publishing such papers. So the interesting question is, if AI can write better papers than particle physicists, what will happen? Good thing I don't work on that anymore. Nuclear power is expensive and takes too long to build. This criticism is partly true, as I explained in an earlier episode, though much of the problem is caused by safety regulations. Yes, turns out that asking that a nuclear reactor please not melt down does add a few pages to the paperwork. Small and modular nuclear reactors are supposed to make nuclear power faster and cheaper by streamlining production. They are becoming increasingly popular, but if you look at the facts, they don't look good. Small modular reactors typically produce a few hundred megawatts of power. The idea is that you can transport them so you can produce them in a factory and then ship them. Once at their destination, you combine them until you've reached the desired power. Kind of like IKEA's modular sofas, but radioactive. Interest in small modular reactors has been booming recently, as many nations realize that storage capacity and grid upgrades which are necessary for renewables are too slow to come by. According to the International Atomic Energy Agency, there are now more than 25 countries investing into small modular reactors. The US government launched a dedicated program already in 2019. The UK government launched one the same year, and just last week they topped up the funding. The Indian government announced in September that they have plans to build up to 50 small reactors in the coming decade. Even the European Commission has now at least formed an alliance that plans to formulate a plan with a roadmap that will facilitate the establishment of an academy and so on. If we're lucky, then by 2030 someone will have read that document. This is happening not least because many companies are wondering how they're supposed to power all their data centers that AI is making increasingly more energy intensive. Amazon just announced last week that they're investing into 3 different US companies to explore the developments of small modular reactors. And Google announced likewise they've made an agreement with Kairos Energy. Small modular reactors could also be useful for energy-intensive industries such as the production of steel, concrete, and the crushing weight of existential dread in the face of unrealistic net zero plans. But if you look at what's been done so far, that isn't promising at all. The first US plan for a small modular reactor was the mPower project. It was launched in 2009 and should have become operational in 2018. Instead, it was cancelled in 2017 after the costs almost doubled to $500 million and the Department of Energy refused to eat up the bill. Then there's the American company NuScale. In 2016, NuScale CEO John Hopkins said that the company expects to deliver its first project of 12 power modules for an overnight price of approximately $3 billion, with commercial operation commencing in 2024. But NuScale gradually shifted the starting date to 2030, and the estimated cost more than tripled, eventually exceeding $9 billion. Then, in November last year, they terminated the project entirely. You might hope that these are isolated cases or specific to the US, but unfortunately they are not. The Institute for Energy Economics and Financial Analysis in the United States has collected the numbers in a recent report, and they're really depressing. There are currently only 3 small modular reactors in operation, 2 in Russia and 1 in China. They each cost more than 3 times as much as originally estimated. One that's under construction in Argentina has now exceeded 7 times the planned cost. It's the same thing with small modular reactor projects that are still underway, such as the one from Hitachi or X Energy. That's one of the companies that Amazon just invested into. The costs are doubling, tripling, quadrupling, and more. Why is that happening? Partly I think it's because companies have an incentive to underestimate costs if looking for investors, but it's also because they have a hard time coming up with reliable data to make good estimates. And how could they, seeing that there has been so little technology development in the area in the past decades? On top of that, you get inflation and increases in labor costs. And the issue is not just the cost, also the time to completion is much longer than anticipated. For the few cases for which we have data, it took on average about 3 times as long as planned. Instead of 3 to 4 years, it was more like 12 years. Now one might hope that things will fall into place once the research and development has been done and these devices can be mass produced. But there are now so many companies offering small modular reactors, they might never have a chance to produce many of them. You all know that I'm very supportive of nuclear power, so please don't take this video to mean that I've become anti-nuclear. But we need to look at the facts even if we don't like them. And if it doesn't work out with the small nuclear reactors, we can always count on the most reliable of all renewable energies, hope. Is space-time doomed? You've asked me over and over again what I think of this or what it even means. And what's going on with the amplitude-hedron? I think the time has come to finally talk about it. The reason I didn't talk about this previously is that I think it's not remotely as interesting as the headlines in certain magazines would want you to believe. And what could possibly be worse than destroying the enthusiasm of a science lover? So with many apologies, but I think the only reason they write about this at all is that nothing else is happening in the foundations of physics. The amplitude-hedron is an idea that was introduced about 10 years ago by Nima Akani Hamed. I've met Nima a few times and I'd put him among the most intelligent people I've ever met. Witten Penrose level intelligence, somewhere in the range where IQ scores become meaningless. I don't understand what he's doing in any depth, but I think I can at least help you to put his work into context. On the face of it, the amplitude-hedron is a way to simplify calculations in particle physics. You see me using this infographic for the standard model at least 58 times. If you haven't, you should now rewatch all my videos. But mathematically, the standard model is what we call a quantum field theory. It's a framework that tells us what happens when 2 particles or more interact with each other, at least in principle. I say in principle because while we have the maths for it, we can in many cases not actually calculate much with it. It's just too complicated. And the formalism that we currently use, figuring out what happens when 2 particles or more get close to each other, for example, because the LHC slams them into each other, requires solving a lot of integrals. And when I say a lot, I mean tens of thousands of integrals or more. There's no exact number because the more precise you want your prediction to be, the more integrals you must solve. Particle physicists usually do this with Feynman diagrams. But Feynman diagrams are just a way to keep track of these integrals. Physicists often interpret them to mean that there's one particle going in and then it hits another particle and that creates a virtual particle and so on. But that's just words. Really what Feynman diagrams are is a funky way to write integrals. The amplitude-hedron now is a better way to calculate all those Feynman diagrams. Loosely speaking, it's an says that the integrals are not all independent of each other. You can collect many, sometimes thousands, together and describe them as a polygon in a higher dimensional space. From this polygon, you can calculate amplitudes from which you can calculate probabilities of measurement outcomes. So a polygon to calculate amplitudes, hence the amplituhedron. The original version of the amplituhedron couldn't be used for the Standard Model, but for other quantum theories that don't describe what we observe, like supersymmetric ones and so on. Mathematically interesting, yes. Physically, not so much. But in the past decade, this research program has grown, and a couple of months ago, the group around Akani Hamed put out several new papers. In these papers, they explain how this approach can also be used without supersymmetry and for some composite particles that actually exist, such as pions. And this is all well and good. The issue with all these Feynman diagrams is indeed a long-standing problem that's holding back our understanding of particle physics. And it's plausible that there are better ways to do the calculations. But in the end, it's just a better way to do calculations. That makes it sound rather boring, and that's why some popular news outlets have tried to make you believe that it reveals a deeper truth, namely that space-time itself doesn't exist. The rationale for this claim is that amplituhedra are not objects in space-time. They live in this abstract higher dimensional space, yet they still encode properties of space-time. For example, that interactions between particles can only happen if the particles meet. This is called locality. So if the amplituhedron can tell us something about space and time and the particles in it, maybe what's real is this amplituhedron and not space-time. Hence the idea that space-time is doomed. It's about to be replaced by something else, like the amplituhedron, or depending on whom you ask, loops or hypergraphs or 8-dimensional carrots, who knows. I think this is all nonsense, and little Albert agrees. For one thing, quantum mechanics, a theory that's more than a century old, is not a theory in space-time either. It's a theory in an infinite-dimensional Hilbert space. So if space-time is doomed, it's been doomed for a long time, and no one cared. More importantly, one shouldn't mistake maths for reality. We say space and time are real because they're useful to describe our observations. We know that they are, amplituhedron or not, so they'll remain real. I agree that it's possible that reformulating particle physics with the amplituhedron will help making it compatible with Einstein's theories of space and time. This could be because maybe if you make the amplituhedron more complicated, then you also get gravity out of it. But so far, no one's managed to do that. So space and time are fine. They just politely ask that you respect their privacy. And my attitude to the amplituhedron stuff is at the moment it's potentially useful, but let's wait and see. It might not be the savior of physics, but it might make those thousands of integrals slightly less annoying. And sometimes that's really all we can ask for in life, isn't it? Do black holes destroy information? This was supposedly a huge mystery that physicists wanted to solve to understand the universe with big implications and so on. Or so popular science writers wanted you to think. And then the big mystery just fizzled away. Whatever happened? Let's have a look. The biggest problem with black hole information loss is that it's not about information. So please don't get hung up on the question of what information means. It's totally irrelevant. The issue is that Stephen Hawking found out that black holes can decay by emitting radiation, which is now called the Hawking radiation. According to his calculation, this evaporation process is irreversible, which means that you can't tell from the final state of the decayed black hole, which is just a bunch of radiation, what formed the black hole or what fell in later. To put this differently, there are many initial states that lead to the same final state in black hole evaporation. What physicists mean by information in this context is just all the details that describe the initial state which get lost. It's not what we usually mean by information. Really, it'd better be called the black hole irreversibility problem. It's a problem because the irreversibility is incompatible with quantum physics. In quantum physics, everything besides the measurement should be reversible. Yes, that means if you burn a book, that is a reversible process in principle, unless you actually want to look at the book. In principle, if you knew all the details about the particles in the smoke and ashes and so on, you could calculate what was in the book. Of course, you can't do it in practice, but this is theoretical physics. The issue is that if a black hole evaporates, the irreversibility happens before the measurement, and that creates a mathematical inconsistency. It's the sort of stuff that keeps theoretical physicists up at night. The reason this happens is not the horizon of the black hole. The irreversibility happens because Hawking radiation is made of particle pairs that are entangled across the horizon. One of the pair falls into the singularity. It's gone and doesn't come back out, end of story. This is what causes the irreversibility, and it's what ultimately destroys the information. By the way, this video comes with a quiz that lets you check how much you understood. But wait, I hear you say, there isn't really a singularity inside a black hole, is there? Well, no one knows for sure, because despite what they say, it's not like we send our grad students there to check out. But yes, physicists widely believe that the singularity inside black holes just means that the mathematics breaks down. We'd need a theory for the quantum properties of space and time, a theory of quantum gravity, to accurately describe what happens near the black hole singularity. And we don't have such a theory. So it's always been obvious what's wrong with Hawking's calculation. It doesn't take into account quantum gravity. It's also a process that we can't experimentally test, because the Hawking radiation of the black holes that we have found is far too weak to be measurable. In the absence of both theory and data, physicists made up lots of stories about what might happen in black hole evaporation. Maybe black holes don't entirely evaporate but leave behind remnants. Maybe information can't ever fall in. Maybe it bounces back at the singularity. Maybe it comes out with the radiation after all. Maybe it sits at the horizon. Maybe black holes aren't real, and so on. And then popular science writers created this big mystery around it. Now, in the past couple of years, there have been some papers claiming that if you take into account as much as we know about quantum gravity, which isn't much, but at least something, then it looks like there is actually information in the Hawking radiation after all. The authors of this work claim that this is enough to get all the information out, so there never was any problem to begin with. I think they should have called their paper Much Ado About Nothing. I'm somewhat skeptical that this will turn out to be mathematically correct, because it'd mean that no information at all hits the singularity, and I don't see how this can be. But the truth is that I don't really care, because we'll never find out what the right answer is in any case. And even if we did, it wouldn't matter, because it won't be useful for anything. Really, the reason I'm telling you about this is that I used to think this was interesting, because solving this problem was supposed to teach us something. But the more I thought about it, the more I realized that there's nothing to be learned here about nature, even in the best case. It's not even philosophically interesting. It's just a bunch of theoretical physicists fighting about whose maths is the prettiest in a contest that'll never be decided by data. So what's the point? Well, points are singular, so one could say that the entire point of quantum gravity is to be pointless. Thanks for watching. See you tomorrow.